Hello there. So today we're going to develop an LED driver. That means that we are going to develop a constant current driver. Also, it's going to be a so-called SEPIC driver, single-ended primary inductor converter, which means that the LED voltage can be lower, equal, or higher than the input voltage. We will develop this around a switching converter IC from XLSemi. But yeah, let's first just find out which IC exactly we should use. For that, we go to LCSC, and then we're going to search under power management for DC-DC converters. And up here, I'm always using XLSemi devices because they work properly. They have many different kinds of converters, and they're not too expensive. And you most likely see them in many different Chinese DC-DC boards. So we're going to go ahead and we want a converter which is boost flyback, buck, or anything close to it, because you can always use a boost converter and make it a SEPIC converter. You all only have to think about certain aspects of that. For some reason I cannot really get many of them selected, or do I? It's only 6 selected. That's not enough, I think. Well, let's just check if we're gonna find the right one. So what we want to have is a low feedback voltage. We're going to use the output path from ground with a low value resistor to set our current, and there's a feedback voltage that we have to achieve in order to get it regulated. To find the exact feedback voltage, we'll have to do some research. So here I have something called XL6006 that could be correct, and I think this is the right converter. Wide input voltage 5 to 32 volts, output voltage up to 60 volts, 0.22 volts feedback, which is great, and high efficiency, and also 5 amp maximum switch capabilities. Let's just look what else we need for that. As always, yeah, a diode would be useful because this is an unsynchronous converter. And also we need an inductor. Also we need a lot of capacitors and, well, some resistors, some passives. So first of all, we found out that we use the XL6006. This is the part number. We're going to go ahead and check that in the SMT parts library to find if there is a version and which version is actually available. If this wouldn't be available with the parts number, I would search for the manufacturer part number, and maybe we would get one which is available, but that part here seems to be available. So let's just go to our EasyEDA and start a new project. Actually, I want to make a new project, and we call it SEPIC LED driver. Please log in. Well, that doesn't work out properly. Why do we have to log in? Come on. I think there might be an issue with JLC or EasyEDA. Let's just check. Make a new project. LED driver SEPIC. And then save it. Am I not logged in? Oh, wait a minute. Well, okay, I re-logged in now, and we're going to create a new project. SEPIC LED driver. Save it. And here we are. Now we can go ahead and get this part number, copy it, and we try to place the component. So there's the part. I always try to get the SMT assembly parts, so if you would like to get it assembled, you can easily have that done for a very low price. No, I'm not sponsored by JLC, LCSC, or EasyEDA or whatever. I just like the way they do PCB and electronics. And what else we need? We need a Schottky diode. If we get 60 volts on the output, probably 70 volts if the regulation is not completely accurate, and it's open circuit, we should use a high voltage Schottky diode. And also we have to keep in mind that, yeah, if there's no load attached, it will always boost up the voltage. This is a SEPIC converter. It can also step up the voltage. So even if the input voltage is just 5 or 6 volts, the output voltage could be 60 or 70 volts if it's open circuit. It's going to regulate down to a current, and it's going to increase the voltage as high as it can until it reaches the demanded current. So let's just check if we get like a 100 volt Schottky diode, because that's just what should be useful. Well, I cannot find one here. Maybe we can use an SS310 as a basic part, because that's free for assembly, or SS210. This is marking for Schottky diodes. The S is the name of the, like, it's a type, it's a Schottky diode. I'm not sure entirely what it stands for, but 2 stands for 2 amps and 10 stands for 100 volts. So, well, we could use this as a basic part. Sure, it's only capable of doing 2 amps, but without additional cooling, I wouldn't give it more than 2 amps anyway. And also what we can do is we can use 2 in parallel, not for increasing the current, but increasing the thermal capabilities, because this diode is not, like, it's not big. It cannot really, like, dissipate a lot of heat easily. Also, what's useful is a capacitor for the input and output. To keep the parts list low, let's just use one type. The output should be able to handle around 100 volt. And yeah, let's just search for 100 volt capacitor. We need an SMD electrolytic, because otherwise we won't get a capacity. I'll look at the capacity values here, and I'm seeing 47 microfarad as the maximum value we can get. And that's why I'm gonna enter this part here. For the input and for the output, I would use 3 on the input, 3 on the output. Just make sure we get some good filtering, and also it's useful to use an MLCC, which is a multi-layer ceramic capacitor, to suppress some high frequencies. And let's just see if we get 4.7 microfarad at 100 volts. That's a lot. I think the maximum we can get is 2.2 microfarad or 1 microfarad. Yes, 1 microfarad. I would also assemble this part just to make sure that we get some clean output and we don't induce a lot of ripple on the input. Let's just use 2 of them. Also, they have extremely low ESR, which means yeah, it's gonna make the thing a little bit more efficient and not let the electrolytics heat up too much. So we got a diode, we got a switching converter itself, we got input-output capacitors. We also need an inductor for the switching converter. And as we have seen before, we need 47 microhenries. You can go one step lower or higher if you wish to. You can go 33 microhenries or 68 microhenries. It will be okay, and generally going higher is better than going lower, because the time to charge up the inductance is higher, so the circuit has actually more time to react to high currents or to spikes. Also, you have to see that it stores more energy, so as a downside, you will have slower response time for the output. But for an LED supply, this is not really that critical. If you have less fast response to transients. We search for power inductors. Let's just get one which has a lot of current capability, which is also available. So that's the only part I can see right now that's available and got like 3 amps capability. Let's just check how the resistance of it is. With 145 milli ohm, it's high. I would like to see something with lower resistance, like maybe this one if we're lucky. It's 142. Why is it so high resistance? We could go lower here. But, well, these parts are not assembled. Yeah, if you can, go with that part. If it's just 75 milliohms, but, well, it is a more efficient part after all. Well, let's just use that one to give you some more output capability, maybe? Well, you know what? We only use a 2 amp diode, and we like to make the output to maybe around 1 amp. So it's a 1 amp LED supply that can supply LEDs with lower or higher than input voltage. Now let's just go ahead and use, now let's just check this one if this is got less resistance. So with 160 and this is 75, that appears to be the most efficient part. So let's just go ahead and use that one because this will gain us the highest efficiency. And because we make a SEPIC converter, we need 2 inductors. And actually, we also need a pair of like additional capacitors. These must not be of as high of a value, but they must have a low ESR. That's why I use 2 LCSCs and just 1 of the normal electrolytics. If we have a design output of around 1 amps, having 3 of them of the electrolytics in series and 2 MLCCs, it will give us very good current response. These capacitors, they're rated for I think 400, 300 milliamps. If you got 3 of them in parallel, you can almost add it up. So yeah, if we design it for 1 amp output at voltages up to 60 volts and also up to 1 amp input at voltages up to 35 volts, around that mark, yeah, you can go with up to 30 watt LEDs here, and that's quite a lot. So we use that use them in parallel. Let's just make some basic layout. Also, we need a feedback circuit, and if we go back to the datasheet here and go down to the SEPIC configuration, you will be able to see example setup for SEPIC converter. This inductor is coupled, it doesn't have to be, but you could use one, it will make it slightly more efficient. Well, let's just see what, yeah, they use just a basic setup for SEPIC converter. And also, this resistor here sets the current. Yes, we want to have about 1 amp, and we need 220 millivolts. That means if we go with 220 milliohm resistor at 1 amp, it will drop 220 millivolts. So yeah, let's just use it. 200-ish milliohm resistor. Also, we have to check if the current capability, the heat output, is okay, and for that we just calculate 1 amp at 0.22 volts, which will be around quarter watt, and I think we can use a 1206 resistor, which is good because JLC, they have the 1206 resistors as the biggest resistors for basic parts, so the assembly is basically free. You don't have to have an extra fee to pay. So we go to chip resistors, 1206 basic parts. We search for 0.2 ohms. If we look here, we want to find 0.2 ohms, but we will find 0.1 ohm. So let's just use 2 of them in series, and that will give us around 1.1 amp of output current, and the regulator will regulate it down. So we use 2 of them in series to get the 0.2 ohms. Also, it would be useful just to have a nice output and input terminals, so let's go to LCSC and search for spring clamp terminals. We find them. I like spring clamp terminals because they're easy to access. You can easily connect something to it and, well, yeah, open it up again. We need 2 positions. It must not be able to handle a lot of current. I mean, even the lowest version here handles around 2 amps. And yeah, let's just go ahead and use that part. 7 amps up to 300 volts. That's perfectly fine, and it's very cheap with 5 cents. Where the hell? There it is. There's the part number. We use 1 for the input and 1 for the output. And now that I think about it, let's just go ahead and use a protection diode so that reverse polarity will short the input or output instead of actually blowing our IC or like breaking capacitors. We can also use a fuse. Well, if we use a fuse, we have to use maybe a PTC, so it's a resettable fuse. That will make it less efficient. Also, getting a 60 volt PTC, we have a hard time finding 2 amp model if it's SMD or 1 amp model. So probably let's just search for a normal fuse, like with 5 amps. Like we can get us. I would use always a slow blow for circuits like this because there's some thermal delay. If you give it 5 amps, it's not gonna immediately blow up. It's just gonna heat up very much. And the XL switching IC also got protection inside, but I wouldn't rely on it. So that's a slow blow fuse, 2 amps, 50 amp peak. Well, let's just put it in, and yeah, put that into the input and also to the output. Because of the SEPIC design, we can. Oh, I think I missed something. This fuse is probably not rated for 60 volts. I think it's rated for 32 volts. Yep, so we cannot use this. I'm sorry. That's the mistake I just made. That's the things you have to look out for. So remove that. But we have to use it on the input and the output because the current can be higher or lower than the input current. We don't know if there's an overcurrent situation somewhere. Well, let's just search. Maybe it's not a slow blow, but search for fuses with like 3 amps and high voltage capabilities. But if we can't find it here, we maybe just go back and search for PTC, which might be able to handle the current. Let's just see. We want to have 60 volts and up, and the current to hold should be 1.6 amps and up. No, it should be 1.6 amps and 1.85. That should be okay. It can hold that, otherwise the inductor will be going to an overcurrent situation where it will heat up or just be saturated, and yeah, that will probably trigger overcurrent protection of the XLSemi IC. And here you see it's no SMD part available. Also because of the thermal heat they PTCs produce. But it's nice because they reset themselves. They don't blow and you have to replace them. They are resettable. Let's just go ahead and take this one because it only had 440 milliohm resistance and it's not too big and it's cheap. So let's search for the part number here. This is not an SMT assembly because it's not an SMT part. That's just how it is. But I mean, if you don't like to use it, you can just bridge it, and the way we do that is by using a 0 ohm or 402 resistor. You just assemble it or not assemble it, or just assemble it because it's a basic part. It doesn't cost anything really, like it's 0.1 cents actually. Yeah, assemble it, and if you want to use the fuse, solder it in by hand and remove the 0 ohm jumper. This will make it less efficient, but it will give you some protection. Yeah, so that's the first thing we put in series. And then we have this diode to give us reverse polarity protection. It will short out once the polarity is wrong or the voltage is higher than 100 volts, which is the breakdown voltage of this diode. And let's just see. Yeah, now it's in the right position because yeah, it should be positive up here. If it's negative, the diode will start conducting and short it out. So give us basic overvoltage protection. If you want to have real overvoltage protection, you could use a Zener diode, but that would add up to the BOM. And also, let's just put the fuse on the positive side because it's just good practice doing that. So that's our input side with filtering and protection. Almost like finished. And yeah, try to put the MLCCs closer to the switcher because they will have the lowest resistance and give you the best response close to the IC. And then again, make sure that port 2 is positive, just also to have like pin 2 of the spring ground terminal, just to have good practice, and also fuse the upper positive, just because, well, yeah, again, it's good practice to go with the positive for protection. And with the negative, we have to watch out, and I actually have to look up if they put it after the capacitor or before? Okay, so this is weird. They use the feedback. Okay. So the capacitor is actually going to ground. So that's okay, and it's not actually connected to the output. Okay. That's weird, but well, let's just let them do that if they want to have that. And these two resistors setting the current are here. And also you can go for any different value of resistors. I wouldn't go with anything that will enable for more than 1 amp, so I wouldn't go lower in value, but if you just bridge one of the resistors, it will only be 100 milliohms, and that will trigger at, well, actually, you have to go higher in value, higher resistance, because otherwise you will increase the current. I would go lower in current, lower than 1.1 amp, but I wouldn't go higher necessarily, because that's probably going to blow the fuse if you have it inside, or it will saturate the inductor, which is only rated for, let's see, 1.6, 1.8 amps. Yeah, I wouldn't like to have that like at full peak power. This is not efficient, and it's also going to reduce the lifetime. And yeah, use this one here too, so the output will be protected against reverse voltage, and connect directly to the pin, not in between the resistors, because they will just unnecessarily heat up. And okay, these two things, this will be ground, and it will also be our feedback voltage. And just so that the output is a little more filtered directly here, like that the feedback values are not just too spiky, I would go ahead and use 100 volt MLCC. Maybe we get a basic part. Nope, we don't get one. Is there like higher voltage value? I like to have an MLCC with a low value that just is in parallel with that, and it removes some of the ripple close to it. Basically, we make it in parallel with feedback, like in ground, connected between feedback and ground, just to remove some ripple and give it a better response. But I think it's okay like that. If they don't have it in a basic design, it's for driving LEDs, it's good enough. So yeah, we just did that, and also make sure the MLCC is close to the switching IC. And what I do is I just make the schematic in a way that I would like also to design the PCB afterwards, just so that you have a guideline to where to put what. And yeah, this is the feedback voltage. We can go ahead and wire that up to all of our parts. Yeah, this is grounded. This is also grounded, and yeah, for sure this is also grounded. The enable pin, you can use it to dim the LEDs. And actually, what we're gonna do is we are going to make the thing dimmable. Yes, there's data sheet actually. Do they have an example for that? Yes, they probably have one like here. They use resistors and give it a signal positive, like, yeah, if the feedback voltage is higher than 0.22 volts, it's going to disable the output. You could also use the enable pin, but it's just for enabling and disabling it, and I'm not sure if this is fast enough if you want to use it with PWM. Probably there's some delay and some soft start, which will just make it behave weird. So what we're going to do is, yeah, in series with the feedback voltage, we're going to use 1 kilo ohm resistor. You can use like 4 or 2. Let's just make it big, because if you want to assemble it by hand, it's just useful to have a big capacitor or big part, because yeah, otherwise it's just a hassle. So yeah, that will still give us high enough frequency response on the output. And yes, also on the feedback, we're going to use a diode. normal diode, general purpose diode, which if the voltage on some pin is higher than the 0.22 volts plus diode drop, so 1.5 volt upwards, it's gonna disable the entire switching thing. And to do that, we're going to protect it also with this resistor, so there's not too much current flowing in a failure event. So yeah, this will be connected to feedback pin with the diode, and here we're going to connect the PWM DIMM signal. With the 1 kilo ohm, it's also protected against too high voltages. You could probably feed 5 volts from Arduino into it with no problem. Also, 10 volts should probably be okay. With the 1 kilo ohm and yeah, the clamping diodes on here, it's gonna be able to handle it. But don't, well, let's just check it. How much is the maximum voltage on the feedback pin? The absolute maximum ratings are listed in the data sheet, and feedback pin voltage, yeah, up to VN. Yeah, you can go high on that, especially if you got a series resistor. And now the feedback voltage, we could use a nanofarad capacitor here to filter it. I'm not sure. And actually, if you just use low voltage for dimming, like up to 10 volts, a capacitor like with low values would be enough. But I would like to use an X7R capacitor with probably 10 nanofarads. And what's the maximum voltage we can get? 50 volts and as a basic part? Yes. Let's get a 805. Let's try to get a 1206. So the smallest parts are like 1206. This one is a 1206 capacitor, 10 nanofarad. Yeah, let's just use that close to the switching converter so that the ripple is not going to influence it too much. If you use very high frequency PWM, just remove that if you have any issues. So the PWM is inverted. If you give it a high voltage, it's going to disable the driver. If you leave it floating, the default value is just maximum current. Okay, so yeah, we must just now do the actual switching part instead of the input and output stage. The PWM DIMM is not actually connected to anything now. We have to see if we use like a jumper or something. I think it would be nice to use a normal male-female header, like you know it from the Arduino. We just use 2 of them, one for ground and one for the signal. Yeah, something like this. Yeah, let's just use the open, like the non-open contact, because it could short out something. Just pierce your 2.54 millimeter DuPont cables or whatever they are in. And yeah, let's just connect that here. And we can actually move this labeling. Give that the PWM DIMM, and the other one goes to ground. Okay, now let's just make a label for the switch. So we're gonna use that many times over, so we just don't have too big of a like input-output hassle. And yeah, the email pin, we could maybe also use it, but I think it's floating high. Floating is default high, and I think they leave it floating at something close to the input voltage. And you could potentially connect it to another Arduino, especially with a series resistor, because I think the pull-up internally is very high ohm. But if the like open circuit voltage on the enable pin is like the input voltage and it's like 30 volts, I probably wouldn't like to connect it anywhere close to a microcontroller. So we just leave it like that. You could use a high voltage NPN and pull it low if you get another high signal, but I think if you have PWM input, it's good enough. Okay, so that's the output stage, that was the input stage, and now there comes the more part where you really have to concentrate, in quote marks. And this is actually, we also label the input. input voltage. And we have to concentrate, and this is actually the design of the switching part itself. And as stated before, we go down to the part where the SEPIC converter is listed. Just have to find it, and yep. So between V in and switch, we connect one inductor. This is our first inductor. This is that one. V in and switch are connected with an inductor. Then we have between ground. Oh no, then we connect a capacitor. I just have to look up what is positive, what is negative of the capacitor. Man, I always mix it up. No, that's positive. Okay, so we connect the positive to the switch pin. And now also make sure to connect the MLCC closest to the inductance, because that's where the highest current is going to flow for the short amount of time. Okay, so one is switch and the other one goes to the other end of the inductor. Okay, which then goes to ground. Okay, let's just do that. Okay, so that goes to ground. It goes to the negative of the capacitor, which then the positive goes to the switch pin, which on the other side goes to input voltage. Okay, now that we got that sorted out, we need the diode, and yeah, the positive output is gonna be like this, and it's going to be connected up here. Okay, and this will be our output voltage right there. Let's just mark it as output voltage. Okay, so I think we actually finished the entire design. We can make that smaller just so that it looks nicer. Well, that was a little low. 1000 should be good enough, and 450 maybe. Yeah. See, that looks. Let's make it 950. Make that look a little nicer, and yeah. Just for good practice, actually go ahead and make some text here, which means input filtering and protection, or make it protection and filtering, because that's the actual order, and this is output filtering, protection, and feedback. And it's not the input, it's the output. Well, yeah, so just people know if they look at it what the actual part is doing. So yeah, make it a little smaller, just enough that you can easily see it, but still have some space to look out for everything. Yeah, that was stupid of me. Let's just make it bigger again. This is just nonsense, just to make it look clean, and if someone looks at it, the person exactly like knows what is happening. So that's sorted out as the filtering parts, and yeah, you could go ahead and make this small part here called PVM dim for this circuit here, so people know that's for dimming, and this here is just it's the converter itself. So let's just check again. 2 is the input voltage high, like the positive. We put that into fuse with a bridge that is set by default if you get it assembled. If not, you could, like, if you don't want to have it pre-assembled, you can go not to add it on the BOM. Protection diode, the output is the same protection diode, and positive the capacitors. Yes, the feedback, yeah, from ground we go here. That's the output current it's gonna see. We give it feedback voltage with a basic OR design, OR gate. And yeah, we have a dim functionality here too. In open is not connected, ground, switch. Feedback voltage goes here with a 10 nanofarad bypass just to filter out some spikes, and the input voltage is going there. Now let's check again. The input voltage comes, it goes to the switch for one inductor, then the positive capacitor goes to the diodes this side. This diode's outside goes to the positive, and from the side of the full of the diode, we also get one inductor to ground. Yes, this is the basic SEPIC design. Let's just save it again, make some checks. All nets are connected, all parts are on there. And yes, that should be it. That should be your 1.1 amp LED driver with input voltage of, let's make it 6 volts to 35 volts. 36 is the maximum voltage. I wouldn't go that high. It's the absolute maximum. I would go 6 volts to 35 voltage volts. And the output voltage is up to 60 volts. But, well, you cannot run it at 60 volts if the input voltage is lower than the output voltage and there's a current limit of 1 amp. Yeah, I mean, yes, the fuse is only going to blow at 1.8 amp, but, I mean, you probably could give it 1.5 amp on the input, which would result to something like 45 watts at 30 volts. But, yeah, just make sure that the output is probably, should not be like a 60 volt LED, because if it tries to put like 66 watts into the output, the input is just not going to handle it properly. So the output I probably just suggest like what, something between like a 5 watt and 25 watt LED, so you're safe with running it from 24 volt lithium or 36 volt power supply maximum, but not a 36 volt lithium, because that's going to be charged up to like 42, 43, 44 volt once it's fully charged. This is designed for 12 volt and 24 volt input supplies, basically, and an output LED of whatever, 5 to 10, maybe 25 volt if you go with a 24 volt battery on the input. And yeah, that's just the finished design. I mean, you could beef it up if you use a bigger capacitor on the output and input, also if you use bigger diodes and more chunky inductors, but for the basic design, that's just good enough here. You could always like improve on it. Let's just make a PCB out of it. Apply a rectangular PCB, that's good enough, but where did it go? Like, for some reason it went down there. Okay. Putting it on there. It would possibly work if you used a router, auto router. It's not too much of a hassle, but I wouldn't recommend doing it. Well, now it's just a matter of like laying it out. You can do that if you want to. Whatever layout you want to have, just go ahead and try to make it. And yeah, I mean, now that you designed the PCB or the schematic itself, you know how to design the PCB. Because you know where the basic input and output is and why certain parts are where they are at, and that just helps with the basic layout process right now. So this one is ground, yes, it is ground, and it's the input protection. I'm just gonna make some basic layout decisions here to make it look clean and just get a steady design upon it. Make a clean design and protect the design. Like a safe design that's going to be able to handle all the thermals that we're gonna see at the polyfuse, for example, because at around 2 amps the current it can hold, it's gonna dissipate around 300 milliwatts, which is not nothing. It's actually quite something, and yeah, it can heat up capacitors, which is not good. I mean, these ones are rated for 105 degrees, 5,000 hours. So at 85 degrees, they're gonna last 2 to the power of 2 times as long, which is 4 times as long as 85 degrees, and they're not gonna experience 85 degrees. And 20,000 hours is quite a good lifetime. And then it's not just gonna like do nothing; it's still gonna be able to hold up. It's just not gonna be probably as efficient, and also we're gonna have problems with some ripple on the output. But for LEDs, usually it's not too big of a problem, especially if a switching a frequency like that is like in the 100 kilohertz region. It's not going to be anywhere close to the 50 or 100 hertz flicker you're going to get on some cheap LEDs, and that's really annoying. I know that. Is that the... no, that's the filtering. What is that? That's the input voltage again. I think we used 3 capacitors on the input and the output, and some MLCCs. well, where's the MLCC for the output? That's the output voltage, MLCC. Let's put that close to where the boost converter is going to be. Also, we will have to use these two resistors just to get the feedback voltage going. And what is that here? That's the resistor for getting the dim signal for the PWM. Okay, and these two resistors are actually the current shunts. Okay, let's go ahead and put them here so that we have nice output stage. That's gonna work. They're also gonna get a little bit warm, so all the parts that are gonna get warm, like the fuse and the resistors, are in one region, and they are kind of separated from the capacitors. And yes, these two belong to the feedback stage. Also, you have to keep in mind that the feedback shouldn't not be close to inductor wires once we lay it out, because the inductor wires or inductor traces are going to induce some ripple into the feedback, which is very high ohm, low impedance, and this is going to mess with the output. So let's just make sure this is not going to happen, and yes, get these capacitors up to the right spot so that we don't use too much of the PCB area. Okay, this is going to be the SEPIC capacitors that enable the SEPIC functionality, and this is the feedback voltage. Let's just put the capacitor close to the switching converter, because otherwise, yeah, it will not really help with the ripple removal. That's another input capacitor. Yes, yeah, it's kind of tightly packed, but for the SMT machine at JLC, it's gonna be good enough. Okay, that was not good for me. Let's just do it like that. Increase the PCB here, and yeah, try to make it the perfect size for our device. Not too big, not too small, and yeah, able to cope with all we want to have. Okay. Well, there's also, you can add like screw holes if you want to. Let's just like put some, what, M2. Oh, that was stupid for me. Somewhere, I mean, you could put it here because there's just space, but also if you can make it bigger, add it like on top of here. If you go ahead and put it there. I mean, I don't need it, so I don't put it in here, but you could do that if you want to. Yeah, and just lay out the rest, and once you've done that, I mean, that's just the basic layout. This feedback circuit here should probably go also close to the switching converter, but not close to the inductors, so probably something like this, and then just make sure that the inductors don't really touch anything close to the feedback area here, so that with that it's kind of protected against that. There's one inductor that needs to be in, that's this inductor, so let's just put that here. Keep the traces very short, please, with all of the switching circuitry. All kinds of weird things are going to happen if you don't keep the wires or the traces short. Okay, that seems to fit nicely. And yeah, that's inductor. Well, okay, this capacitor is probably gonna heat up more than I would like it to. So yeah, try to I'll make the low ohmic thing here. Go here. The feedback. Yeah, it's probably not best practice putting it somewhere close where the output voltage is gonna happen, but layout wise it just kind of makes sense now. And the diodes just in parallel to dissipate the heat better. Oh, we can use them. Well, these are for the output. Okay, now we're gonna have a struggle because we want to have them close to the output, but also close to the inductors, and now we stretched it a little long, and it's not gonna be perfect, but well, yeah, you can make a layout like this, and the size of it's gonna be like 12 centimeters times 3 centimeters, which is okay for an LED driver that can really output like 10, 20, 30 volt continuous without blowing up, and it's high quality parts. It's much better than the stuff you will get from China. And yeah, you can go ahead and use that on probably the top silk screen, and yeah, just make plus in minus like this, and then plus out minus, so you know what to connect where, and then you go ahead and do some PVM and then ground, and you could do it like this on here, so you know which pin does what, and like it's just a matter of what you want to do right now and how the final product should look like. I mean, I can't really tell you about that. I just made like the basic design here. Yeah, if you want to route it, you can go ahead and use the auto router, and actually I'm not good with knowing stuff about traces in millimeters. I just know about mil and know that 20 mil should be enough. And actually, if they use vias on here, let's just tell it to use 35 and 25 millimeter, and maybe 25 or 22, so we can really do it. Clearance, yeah, 7 or 8. Well, should be good. Let's just let the auto router run. It runs on the server of JLCPCB. You can also go ahead and download the auto router and run it locally. You can also configure some additional stuff on it, and it's much faster usually if you have like an Intel Core i5, i7 from the last 5 to 10 years, or an AMD Ryzen CPU. Because the server is actually waiting. I mean, it's full, it's packed, many people trying to auto route on there, and it's just gonna take a lot of time till you get a slot for letting it route. If this is not gonna work, we'll have to start up my local auto router, which I just downloaded. Yeah, let's just go ahead and start it. Yep, and stop it again. Auto route it locally, automatically selects it, and that should be. Why is it taking so long? If there's some issue right here, it should have routed it properly already. Let's just save it again, check for some basic, yeah, nets are not connected, but other than that, there's no problem. Yeah, we can also go ahead and do a ground layer on the front of the PCB and also on the back. Because, yeah, it's just good for electromagnetic interference protection, and it's also gonna decrease the ground path resistance that we have on our PCB and make it possibly a little bit more efficient. Yeah, 0 failed. Actually, we can go ahead and increase the value like to 55 maybe if we're lucky. Just go high and try it out. Yes, it could not route some of the traces. We could manually do it, but if it works fast with the other router, just go to 40, or let's check again if we can use 45. That's also going to help some heat dissipation from some of the pins that we have on there. That's not going to work, so yeah, let's just do 40, the last thing that really worked. And go ahead and check if all the traces to the inductors are great, and they are. I mean, short traces for input and output. Well, here, this is kind of a problem because the output, it goes close. I mean, it goes under the PCB of the feedback, so it's not too big of an issue. It's kind of shielded. The other router did something nice there without even knowing what he's doing, but boy, she is doing. Yeah, now you can go ahead and like make the labeling nice, but I mean, if you look at the product, like we started like probably 45 minutes ago, and now we got a finished LED driver, which is looking quite nice, and it's actually higher quality than most of the stuff we'll get on the market. And getting a SEPIC LED driver, this is gonna probably cost, if you get high quantity 30 pieces from JLC, it's gonna cost like 120 including shipping, and €4 or $4 for such a nicely designed part, which can really, if you give it like attach it to a 12 volt battery, the output can easily handle 10 to 15 watts, now let's say 10 watts, continuously without heating up too much or without having hassle. You can PWM it easily with a microcontroller. It's well made, I'd say. It's higher quality than what you will find if you buy something finished. So yeah, just try to do it, and probably see you in the next video. Yeah, and there's one more thing I forgot about, and that's just going ahead and checking the nets. Yes, they're connected. Components are connected, and clearance. Yes, there's some issue with clearance close to the 0402 parts. Who would have guessed? The easiest thing is just go ahead and like select the part where the problem is actually coming from. So the traces close to that, and just make them smaller, make them like 25, and have a look at it, and suddenly it works. It's still going to be able to handle the 1 or 2 amps, no problem. Yeah, you can also go ahead and do a copper area rebuild. Makes it look cleaner. Save it again. And here we are. Now you can like export your BOM, generate a fabrication file, export a pick and place if you want to order it at JLC. And yeah, it's just gonna be a nice device.